Hello. So my name is Andrew Fielding, and I'm going to be talking in this lecture about acceptance testing and commissioning. And in particular, I'm going to be talking about acceptance testing and commissioning of a medical linear accelerator. So acceptance testing and commissioning sits in the chain of events that occur when you're purchasing, planning to purchase, and then finally going clinical with a medical linear accelerator. So there'll be things like clinical needs assessment, selection and purchase process, and there'll be delivery and installation. And then before you can start using your machine for clinical applications, you need to go through these two processes of acceptance testing and commissioning. And then, of course, we'll also have things like training, and then we'll go into clinical use. And then there's also the periodic quality assurance that needs to be completed to ensure that those standards that we achieve at acceptance testing and commissioning time are maintained. So here we're going to focus on really acceptance testing and commissioning. I'll say a bit about equipment specifications, and I'm going to be focusing on the linear accelerator. So as I've already said, the acquisition of equipment involves quite a few steps. First of all, we have to justify the need for this particular piece of equipment, the linear accelerator. We then need to go and look at the evaluation of different makes and models. So in the case of a linear accelerator, this might be if we're going to get a conventional linear accelerator, this could be comparing Elector and Varian. If we're deciding on a non-linear accelerator way of delivering radiotherapy treatments, we might be looking at tomotherapy, cyberknife, gamma knife. Okay, and this is also true for planning systems. Okay, and CT simulators, for example. We want to be confident that the vendor is able to have a good relationship with the customer. This is usually apparent. You speak to others to find out what their experiences are. And then you will write some specifications that really lay out the details of what your requirements are, the clinical requirements in your department. And then the vendors will have an opportunity to answer these specifications and to demonstrate that they can meet these specifications. And then you're able to make a final evaluation. And of course, there's also the important price negotiations. Okay, these, it's surprising, manufacturers quite often are prepared to negotiate a price. And this process is a shared responsibility generally between the multidisciplinary team in the radiotherapy process. So that includes the radiation oncologist, the physicist, and the radiation therapists or technologists, and also the administrators. But the physicist's role is primarily a technical one, and a scientific one. It's to write technical and scientific specifications, although you will be involved in the whole decision process. The specifications need to be written in a format that the vendors can respond to them item by item, so a sort of list format, point by point. You maybe need to put in specifications in regard to the beam characteristics you want and acceptance criteria that are going to be necessary to meet these beam characteristics, and how you're going to define the beam characteristics and the methods of measurement. Okay, and I'll talk more about some of these as we progress through this lecture. This is particularly, I guess, the case if you're buying an accelerator in a department that already has a number of accelerators, and it's very important that your new accelerator matches the previous ones. Although saying that, these days accelerators are mostly very closely matched anyway. Okay, but you might have an older machine and you want your newer machines to match that. It's important that where possible, we also try and follow national or international guidelines and terminology. That way everybody is clear on what we're talking about. So acceptance testing is something the vendor provides. They'll usually provide a set of procedures that they want you to go through. These procedures are set up by the manufacturer to demonstrate the product meets the specifications, both of its sort of, I guess, its own specifications and also the legal requirements of equipment safety. A general rule, some form of acceptance testing is required on any piece of equipment that is used in conjunction with patient treatments. And generally for linear accelerators, simulators, brachytherapy sources, there's a formal set of procedures that you need to go through. But they may have to be improvised for other smaller items of equipment. So the linear accelerator is a sophisticated piece of equipment that requires several months for installation, acceptance testing, and commissioning. And this is particularly true for some of the modern true beam type accelerators that have multiple photon energies, multiple electron energies, and have the capability to deliver quite complex treatments such as stereotactic body radiotherapy. The installation is carried out by the manufacturer, but the acceptance testing and commissioning is going to be carried out by hospital physicists. So these are usually local-based physicists, but it could be that you get in if it's a new department and maybe you don't have a fully trained or fully employed team of physicists, you maybe have to get external physicists in to do this part of this acceptance testing and commissioning. And it's important to stress here that we can't use the machine clinically until the unit has been commissioned. And that really says that the machine is tested to be acceptable, and also the commissioning data has been acquired to allow treatment planning and dose calculations for patient treatments. It's also worth pointing out here that some of the specialized type machines, like tomotherapy machines, a lot of the commissioning and acceptance testing is done at the factory. So you can, from the point of installation or the completion of installation, the turnaround time to getting in some of these specialized machines can actually be quite quick, because a lot of the data that needs to be collected for commissioning, and for example, tomotherapy has its own planning system, so the data is pretty well defined as to what you need. The machines come off the factory production line very well matched, so they're pretty much ready to go. So one important aspect of acceptance testing is the radiation survey. So once the installation has reached a stage at which a radiation beam can be generated, so the point at which we can switch the machine on and get a radiation beam, we need to carry out a preliminary radiation survey of the treatment facility before we progress. This is done to ensure that during the acceptance testing processes, exposure levels outside the room are not going to exceed permissible limits. Now, at this stage, it's important that we do some sort of a preliminary calibration of the machine output, so that the relationship between dose and monitor units is roughly that we would expect to use in a clinical setting. So that usually means calibrating the machine so that 1 centigrade equals 1 monitor unit under the reference conditions of the protocol that you're going to use for your absolute dose calibration. You will, of course, do a more detailed absolute dose calibration, a more accurate absolute dose calibration later on in the commissioning process, where you're looking to get very good accuracy there. So we need to carry out this radiation protection survey. We need to measure head leakage, an area survey, so measuring around the bunker at all aspects, in all the locations where potentially people are going to be outside the bunker. We also need to test interlocks, warning lights, and emergency switches, so that these are going to be functioning correctly during that acceptance testing and commissioning process. Okay, I'm going to go through a series of specific tests, and this is really to give you a flavor of the sort of tests that we might find ourselves doing during this acceptance testing and commissioning process. It's worth pointing out that this is not in a an exhaustive list, you might find that in local departments they have slightly different ways of doing these tests, but these are the way in which acceptance testing, these particular tests are implemented at a local clinical department in Brisbane. So the first one we'll look at is that of jaw symmetry. So this is ensuring that if we move the jaws to a particular setting, that they are in fact symmetric. And this actually requires a physical measurement with some sort of measurement device like a feeler gauge. And what we're looking for is to make sure that if we set the jaw pairs to, say, a 10 centimeter field, that those jaws are actually at plus and minus 5 centimeters. Okay, and we need to do this for both sets of jaws. The next piece of acceptance testing we might need to do is that of coincidence. So this is done with the gantry at 0 with a rectangular field, and we're going to fix some graph paper on the patient couch, and we're going to ensure that the light field, which is a measure of the position of the physical position of the jaws, and also we can see on that light field the position of the crosshairs, that these all align correctly. And graph paper is a very simple way to check this. Okay, so we're going to, and I'll show some images of this on the next slide. We're going to set up the graph paper, project the light field onto this graph paper, which is fixed on the couch, and then we're going to check the coincidence of light field edges and the intersection of diagonals and positions of the crosshairs. We might find that if we see any significant misalignment in these parameters, then we're going to have to adjust to give the required coincidence. So you can see here in these images, there's some graph paper on the couch. We would project the light field onto this, and then we can just check that everything is orthogonal, that the light field is projecting the correct size. And we do this at different angles. You can see here that this local technique for doing it, they've got a sort of perspex screen which they can put the graph paper on in the vertical plane. And this allows you to test the location of the crosshairs with gantry and collimator rotation, and also the accuracy of the digital field size indicators. So if you set a 10 by 10, this actually is a 10 by 10 field, for example. We can also check symmetry using this technique. This is another, you'll find that a lot of local centres, although you can buy commercial sort of equipment to help you with this process. This is actually a device that was designed locally in-house. This allows you to set up the phantom, or a particular sort of, it's just a sheet with different field sizes on it. And we can check the squareness of the jaws visually by comparison with the markings on this. We call it a phantom, but it's essentially just a board with the fields marked on it. And we would do this typically at a particular SSD. That way we know that if we do it at 100, then we know that if we set it to a 10 by 10, we should have a 10 by 10 field on this phantom or this board. Okay, we do this for multiple field sizes. And also you can see that this allows us to rotate it into the vertical plane. And we can check at the 4 principal gantry angles of 90, 180 and 270. So you can see in these images on the right, for example, you can see the light field projecting onto that board, and we can check that everything's square, the field is orthogonal, but it is just a visual check, really. So there we are doing it at different angles. So on the left is at 0 degrees, so the beam coming from the anterior direction, and then we'll do some laterals. We can also check it from 180 and also from the 270. And this is really just checking that collimators and things don't move and the light field don't change as we rotate the gantry around, and we get some sagging effects maybe. Now, it's one thing to check that everything is orthogonal and square and symmetric with the light field, but of course ultimately what we're interested in is that the radiation field is also meeting all these characteristics and these parameters. So we need to check if we've checked the light field, or we've used the light field to check that all these the jaws are orthogonal, we then want to check that if we use perform a radiation, that this irradiation field is going to align with the light field. Okay, so the simplest way to do this is with film. Okay, and in these examples I'm showing, some of these slides are some years old now, but the principles are the same. We will be using radiographic film. Okay, but of course we can repeat all these days with radiochromic film. So we place the film on the couch, generally first of all with the collimator at 0. We set a square light field and mark the light field edges on the film, and in the old radiographic film we would make little pinpricks, so that would expose the film at the corners of the field. We'd put some build-up material on the film, and then we would irradiate. And then we'd repeat this at different collimator angles of 90, 270, and maybe 180 as well. And we'll be looking to see that the alignment of the light field and radiation beam are close to within a particular tolerance. So that would typically be 2 to 3 millimeters, okay, depending on the protocol you're using. Maybe better, but you would expect to get probably better than that. So here we see that, again, we're using that same device that we used for checking the light field. Now we've just put the film on it. And you can see here we're actually using radiographic film, so the film is light tight inside the envelope. But we can do this these days with radiochromic film. Okay, and we can mark the film to show the edges of the light field, irradiate the film, and then we can check the alignment of the light field and the radiation field on the film when we scan it. Okay, and we can do this for various gantry angles, collimator angles. Okay, remember the collimator rotates as well, and field sizes. Now, another important aspect of the linear accelerator is the mechanical isocenter. We've got this big heavy machine that's going to be rotating around and directing a radiation field towards this isocenter. This isocenter is important because we set the patient up around this isocenter, and so any uncertainties in the position of this mechanical isocenter, or the point at which the machine rotates around with its degrees of freedom, are going to cause problems. Okay, going to introduce spatial and geometric uncertainties into the patient treatment. So we want to be confident that the intersection point of the axis of rotation of the collimator and the gantry are all going to coincide. Okay, and this needs to be checked as we rotate the gantry. The gantry, remember, is a very heavy piece of equipment, and there may be some flex, and we want to check that if there is any flex, this mechanical, it doesn't have any, the mechanical isocenter doesn't actually move. So again, a simple way to check this is with something we can put the front pointer on the linear accelerator. So this is an actual physical device that we can fix on. It's a metal pointer. We can set it up so that the tip is at a particular point. We can set it up so it's at 100 centimeters from the source, so the isocenter. We can then put some graph paper underneath it, and if we just then rotate the collimator, okay, so we're rotating the head of the linear accelerator, what we're looking to see is that front pointer doesn't move around significantly. Okay, and we're looking at sort of around about, we want better than 1 millimeter, 2 millimeters. Okay. The other degree of freedom is the gantry rotation. So in this case, we can use 2 pointers. So you can see in this sort of geometry, we got the front pointer on the vertical plane, which is the collimator rotation axis, and then we'd have another front pointer on the couch in the horizontal plane, and these two tips are very small, and we can make them touch. And then if we rotate the gantry around, what we're looking to see is that these 2 pointers don't move around relative to each other and we're looking for sort of sub-millimeter accuracy here as we rotate the machine around. Remember, what we're measuring here is the mechanical isocenter. And there's some local physicists there actually performing this. You can see that we've got a horizontal pointer and the front pointer, and what we're doing is we rotate the gantry around. We're looking to see that the tips of these pointers are not moving significantly away from each other, and in fact moving with less than 1 millimeter. So again, just to stress, this is the mechanical isocenter. It's the isocenter at which the machine is actually rotating. And there's some more images showing that. So as we rotate the gantry around, we're actually going to be watching and seeing that these very small tips are not moving significantly away from each other. Now, of course, ultimately, again, the mechanical motions are important, but ultimately what's important is that the radiation isocenter coincides with this mechanical isocenter. So we always check the mechanical isocenter first, and then we do some checks to see that the radiation isocenter is also correct or accurate. Okay. So the first thing, again, we can check is the collimator rotation, and we can use film for this. So we put some film on the couch in the horizontal plane. We put some build-up on the film if necessary. And then we set up the jaws to give us a slit beam. So this means that they're going to be very close, a very narrow beam in one direction and quite long in the other. Okay, so we end up with a very narrow slit beam. We're then going to radiate the film. We're then going to rotate the collimator. Okay, re-irradiate the film, rotate the collimator again, re-irradiate, rotate, and you can see here we're doing it at sort of 45-degree intervals. Okay, and what we're looking for is that where these slit beams all intersect, that central point, all the lines intersect within a particular tolerance. Okay, for example, a 2 millimeter diameter circle. Of course, the other degree of freedom we have is the couch, the table, patient table rotation. We can do a similar measurement here. So you can see that what we've got, we do the star test as we call it, similar to the one we did previously. So this time, instead of rotating the collimator, we actually rotate the couch. Okay, and that allows us to get a similar sort of star pattern on the film. And again, we're looking to see that these slit beams all intersect within a very small 2 millimeter diameter circle, for example, or whatever the tolerance is in your acceptance testing and commissioning protocol. We can use a similar technique for checking the gantry rotation. This time we put some film in the vertical plane. Again, we set up a very narrow slit beam, and what we're looking to see is that when we radiate this film, that we end up with we get a star pattern again, and again we're looking to see that the intersection point is going to be it's going to be in a very small localized region in the center. Okay. Of course, there will be some in this plane. We are going to have some divergence of the beam, but we can get a very reasonably narrow slit beam. Okay, to do this test. So here's some images again. These were done in the days of. I say in the days. It was probably only actually around. It was inside the last 10 years, but you can see here. In this test, actually, we've also got the pointer there. Okay, so we've got this the metal pointer, which will show up on the film and allow us to see on the film where the mechanical isocenter is, and we can check that the radiation isocenter matches the mechanical isocenter. And we need to do this in various planes, as you can see here. Okay. The light field intensity, well, this is really something which is required, but it's not particularly useful in practice. Obviously, the clarity of the light field is going to depend on the ambient light level in the room. So if you have the lights dimmed or up, it's going to affect that. So you can use this sort of intensity meter to check the intensity of the light field. Generally, if something goes wrong, with this sort of system, the optical system, the light field, it's usually the bulb goes. Okay, so it's either on or off. Very rarely would you see a sort of loss of intensity over time. But generally, these sorts of things you would notice when you're using the machine if there is a reduction in light intensity over time. Okay, this is another sort of mechanical test. One of the things that's quite important is the optical distance indicator. We use this for setting up the patient. So this actually projects the distance onto a flat surface. And we want to check that this optical distance indicator is accurately giving us an accurate measure of the distance to that surface. So again, this is a sort of local solution to this problem. This is like a little physical block with multiple steps. So you can set this up so that the central one is at the isocenter. So you can use the front pointer there. So the tip of the front pointer is 100 centimeters from the source, the isocenter. And then we move the couch up so that that surface on the step is at the isocenter of the tip. And then we're going to check that the optical distance indicator on the surface of the step tells us that it's 100. And then we can just move the step over and check the optical distance indicator. So when we, at the lower ones, those I think are 10 centimeter steps, we can check that 90 and 80 centimeters and also 110 and 120, the optical distance indicator is accurate over this range. Okay, so the other important aspect, those are some of the mechanical tests, and as I said, those are not exhaustive, but they give you a feel for the sort of things we can do to check the mechanical movement. And there was some radiation checking there as well. We were checking the congruency of the light field and radiation field as well, remember. But also another important aspect is that of X-ray beam performance. And one important aspect of that is the energy of the beam. Okay. Now, this is not as straightforward as it might sound. Now, on a linear accelerator, typically we would have, maybe 2 photon energies, or historically that's what we've had, say 6 and 10 MV, for example. More recently, we've seen accelerators introduced with up to 5 or 6 different photon energies, the variant true beam, for example. But we need a way of actually specifying the energy. Okay. Remember that when we talk about a 6 MV photon beam, that's actually the maximum energy. Okay. Remember, we're generating X-rays using a Bremsstrahlung target, so we're going to get a whole spectrum of energies. Okay. And that nominal energy is effectively the electron energy onto the target, the mean electron energy onto the target, and then we get this whole spectrum, and there'll be a maximum energy, which will be the nominal energy of 6 MV, for example, and then the Bremsstrahlung distribution. Okay, but every accelerator will potentially have a slightly unique Bremsstrahlung spectrum. Okay, these days we can match accelerators pretty well, but there will be some subtle differences. So we need a way of measuring the energy indirectly. Okay, one of the simplest ways to do this at MV energies is to measure a depth dose. So we measure the depth in a phantom, measure the dose at different depths with an ion chamber, typically in a water phantom, and then we can compare the depth doses to tabulated depth dose data. This British Journal of Radiology, 1983, you can see it's quite an old paper now, but this has, for example, a whole load of depth dose data, which we can then look at, and from the published depth doses determine what the energy of the beam is. Okay, our nominal energy, I should say. So one way of doing this is to compare the ratio of depth doses at 10 and 20 centimeters. Then we look at this tabulated, published data, and we compare and we look for the energy of the beam. Okay, and this is something we can check periodically as well to ensure that the energy of the beam isn't changing over time. That's very important. The energy is going to determine the penetration of the beam, for example, and the dose that we're going to deliver to the patient. So we'll have a series of, we'll do these measurements, and then there'll be a, we compare the ratio of the depth doses at 10 and 20 to the published ones, and we're looking for, within a few percent. Okay, and remember, this is just really for a nominal energy distribution. Okay, for the actual data that we're going to put into the treatment planning system, we're going to have to do a more accurate calibration and use clinically measured and use some depth dose data, okay, for clinical use. So the energy of the beam is important. Another important aspect is the field flatness, although of course in recent years there's been the development of flattening filter-free linear accelerators, so we can now deliver radiation fields, we can deliver treatments without a flattening filter. But even these machines typically will also still have the flattening filters in them, so we still need to measure this flatness that we get when we use the flattening filter. So we need a way of defining the flatness. So we measure the lateral dose profile, so we measure with an ion chamber the profile the dose variation across the field, and then we're looking for the maximum and minimum in our profile, and using that we can calculate here in this case the maximum is big M, the minimum dose is little m, and that allows us to calculate this flatness parameter as given by this little formula here. Okay, and we need to measure this at different depths, and what we're looking for is a flatness of, depending on the depth of course, within a particular tolerance. Okay. The other important thing is not just the flatness, but also the symmetry. Okay, and again, we can get this from the lateral profiles. We can just look at the dose either side of the central axis, maybe plus or minus 2.5 centimeters, plus or minus 5 centimeters, and then we compare those doses. So for a symmetric beam, they should be equal. Okay, we're looking to make sure that any variations, the symmetry doesn't vary by, well, again, we would hope to have better than 2%. Okay, much better than that. Of course, we also have to do the same for the accelerator in electron beam mode. And again, we can get this information from depth dose or depth ionization curves. I'm not going to talk about the details here, but we look at the electron beam profile, and we can, from that depth dose profile, we can get things like the extrapolated range, RP, and we can calculate the most probable energy from this extrapolated range. Okay, and we're looking for the most probable energy to be within about half an MeV of the nominal energies, so 6 or 10 or 12, whatever that particular energy is. So we need to do this for all the energies, beam energies that we're going to use clinically. Okay, that's important to stress here. Usually we can measure these using a water tank. So we measure the electron depth ionization curves. So we just do a scan, and then the software even will give us various parameters. It will give us the depth of 100% of the dose, the depth of 90% of the dose, the depth of 80% and 50%. So these are known as R100, R90, R80, and R50. Okay. We also need to check flatness and symmetry for the electron beams. The flatness and symmetry specifications of electron beams are given a number of different protocols. For example, there's the AAPM, task group 25. Historically, this is the one that was being used from 1991. I'm not sure, there might be a more recent one. iCrew also have a set of specifications, okay, for radiation dosimetry for electron beams for over the range that we might use clinically. So this shows you how we would define flatness and symmetry excuse me, for electron beams. So we measure with some film, for example, and then we have we can parameterize our field. This dashed line is the geometric beam edge. Okay, and what we're looking to see is that the isodose lines, the distances between the isodose lines and the geometric beam edge, okay, shouldn't exceed certain tolerances. So the distance between the, for example, this is the IEC specification, the distance between the 90% isodose and the geometrical beam edge shouldn't be more than 10 millimeters, so 1 centimeter along the major axes, okay, so the horizontal and vertical, and 20 millimeters along the diagonals. Okay. The other requirement is that the maximum value of the absorbed dose anywhere within the region bounded by the 90% isodose contour should not exceed 5% or over the absorbed dose on the central axis. Okay. For symmetry, we're looking at if we take 2 points either side of the central axis, then we shouldn't get a variation of more than 2%. This is just showing some examples of the water tank and how we can make these. We can make measurements in the vertical plane, so the ion chamber can scan downwards through the water, and also we can scan horizontally at a particular depth. Okay, so this is a very efficient way to actually make measurements of dose to water or ionization characterize the radiotherapy beam, both for X-rays and electrons. One thing that worth pointing out, that of course what we're doing is we're measuring, as we scan, we're actually going to be measuring at different points in time, and the radiotherapy beam is dynamic. Okay, there will be small variations in the output of the machine, so that means that the symmetry and for example, and the flatness, the depth doses might change, hopefully within a very small tolerance over time. So we can remove these effects by having a second chamber in the edge of the field, and then if we divide these two, and you can see in this image, sort of in the central right there, we can see you can see here where my cursor is, we can see the reference chamber, and then we divide the ion chamber measurement in the water by this reference measurement, and that removes these time varying output fluctuations in the accelerator. So all we're doing is measuring then the actual profile of the beam, either in the depth direction or in the horizontal direction. Okay, we can measure profiles at different depths. You can see there, I give an example of different energies. We might have to do some adjustment of the beam. You can see here, this is a variant machine, so they use potentiometers there. Elector machines, you can steer the beam and set it up. So you might have to, in the initial setup of the machine, you're going to be maybe measuring the dose and trying to get a flat and symmetric beam, getting the depth dose distribution you want by controlling the output of the machine, and mainly the main thing you control is the electron beam onto the target and the alignment of that. Another important aspect is that of the monitor chambers. We need to check that, remember the monitor chambers are in the head of the machine and they're transmission chambers, so then monitoring the output of the machine. What we want to be confident is that the relationship between monitor units and dose is linear. So this is constant as a function of dose rate. So this means we can make multiple measurements at different doses. So for example, if we double the dose, or if we double the monitor units, we would expect to see a factor 2 increase in a dose. If we triple the monitor units, we would expect to see a factor 3 increase. Okay, and we need to check this over the full range of clinical monitor units we might use for patient treatments. Okay. And longer term, we need to check the stability of these, because if something goes wrong with these monitor chambers, they're going to affect the output of the machine. Okay, and that's serious. Another thing we need to check is that of wedges. So we need to make measurements with the wedge in and out of the field. You can see here, and we measure the isodoses, and we check that the wedge angle is correct, the wedge isodose angle. And we do this for a particular field size and a particular depth. Okay, so you can see here we did it at 10 centimeters to check that those isodose angles are as specified. Okay. Here's a list of some miscellaneous checks that we may also do. The couch motion up and down. We want to be confident that this moves around the isocenter. It shouldn't exceed more than plus or minus 2 millimeters. The optical distance indicators, I've already talked about these with that step phantom. Field size indicators, gantry angle and collimator angle should be accurate to within 1 degree. Okay, so as we rotate the gantry around collimator angle, we want to be confident that those are accurate. The lasers, I haven't said too much about those, but lasers are very important because we're going to use those for setting up the phantoms that we use in a lot of our dosimetry checks. So we need to be confident very early on that lasers are actually aligned to the isocenter as accurately as possible. Something else we need to check is that as we add more weight to the table, the couch, that there might be some sag in it. Okay, so we need to put a load of weight on that and check that that there's no significant sag there. That's going to mean that the patient is going to be misaligned around the isocenter. And these days, with the sort of strong carbon fiber couches, this isn't such a significant issue, but it's something we still need to check. Okay, so once we've completed acceptance testing, that's basically saying the machine meets all the specifications that the manufacturers have laid out. But before we can use it clinically, we have to acquire more data. Okay, we have to perform an absolute dose calibration. We also have to acquire beam data and the required parameters for treatment planning. So every particular linear accelerator and treatment planning system combination has maybe a slightly different set of beam dosimetry data that we maybe need to acquire. Okay. And then once we've acquired all this data, we then can do dose calculations within the treatment planning system in simple phantom geometries, and we can compare the measured and manually calculated distributions. Okay. And once we've been through all this process, the linear accelerator is considered commissioned for clinical use. So Khan has quite a nice sort of summary of some of the commissioning data, and a lot of these things we will have done during acceptance testing, but this commissioning data forms the benchmark for which we're going to, for performance, that we're then going to check periodically with our quality assurance program. Okay, so this is the gold standard data that in the future, when we do perform quality assurance measurements, we're going to check that our linear accelerator is still performing to these standards. So we need to do absolute dose calibrations, measure depth dose curves for all the different modalities. So this means for an energy, so X-rays and electrons at different field sizes, and also in the case of electrons with the different applicators. Okay. We need to measure transverse, longitudinal, and diagonal dose profiles for all the different energies at Dmax. That's the depth of dose maximum for electrons and for photons, and also for different applicators for electrons and selected field size for photons, and then isodose curves as well. So you can see just on this single set of 4 data sets that on a modern accelerator, such as a Varian true beam, for example, if we have 5 photon energies, 5 electron energies, this is a lot of data that we have to acquire. Output factors, so this is looking to see how the output of the machine varies as a function of field size, okay, for all the different combinations that we might use. And I say one thing I probably should point out is also complicated these days by the fact that we have flattening filter free. So for every beam energy, photon beam energy, for example, we're going to have to measure it with and without the flattening filter. Okay. Off-axis ratios, the inverse square law. We need to check this, that the dose varies as we move further away from the source. It follows the inverse square law. Tissue phantom ratios. If we're going to be using isocentric techniques, we can calculate these from percentage depth doses, but we're also going to need to do some measurement checks of the calculated tissue maximum ratios. Okay. The surface and build-up dose, this is important. We need to check this and make commissioning measurements of this. And then all this data needs to be entered into the treatment planning system. And we need to perform calculations and check that the measured data, or we need to perform calculations in geometries that maybe we haven't measured and check that, and then make further measurements and check that measurement and calculation match. Okay. We also need to do commissioning measurements for all the special techniques we might use. So these days, of course, this includes things like VMAT, IMRT, stereotactic body radiotherapy, which might use quite small fields, for example, and small field dosimetry is an area which requires a whole new set of commissioning measurements. So commissioning is complete only after the beam data has been input into the treatment planning system and the computer-generated dose distributions have been checked, okay, rigorously. And then we can be confident that when we plan patient treatments, that the machine is then actually going to be able to deliver those treatment plans. So I'm not going to say too much about this, but of course we also have to commission the treatment planning system, verify that its algorithms are correct and accurate, and it's precise as well. We need to verify the precision. And again, it's worth stressing that it's the medical physicist who has the responsibility to oversee the proper use of the treatment planning system and interpretation of the treatment plan. And one important aspect is we need to understand the limitations of our treatment planning system. Okay, we need to understand what situations is our treatment planning system, and then subsequent delivery of a particular plan using the linear accelerator. We need to understand what scenarios is that likely to be least accurate. Okay, so for example, this probably means small field geometries. Okay, if we're using very small fields, low monitor units, which we might use in VMAT and IMRT type treatments, then we need to understand the limitations of our treatment plans. Okay, so that's a brief summary of the acceptance testing and commissioning process that we need to undergo for the linear accelerator system. Thank you.